So hi, my name is Marina Matthaiou and I'm a PhD student at Flow Instabilities and Dynamics at the Technical University of Berlin. And today I will present to you FELiCS. It's not wrong, it's derived from FEniCS and is a versatile linearized flow solver for multiphysics applications. And FELiCS is genuinely a collaborative work, as you can see from the main names on my first slide. And it is recently become open source software due to this team. And this was a really hard process, but we managed from different academic levels, from bachelor students to professors. And when we tried everyone to write his or her own code, we saw that we can manage to adapt the code to one software. And what is FELiCS about? So what we are studying are turbulent flows. And turbulent flows can be seen in many engineering applications in real world, like gas turbines, wind turbines, airfoils of an airplane. And what turbulence has as a characteristic is it's chaos. And we don't want chaos. Because chaos, what it has is causing thermoacoustic instabilities that destroy or cause fatigue of the engines. Or we can hear it sometimes through noise pollution from wind turbines or airplane. And we don't want that. In order to understand how turbulence works, we need to get rid of the noise. And yes, although there is a chaotic movement, we can find structure in our chaos. And you can see here how a turbulent flow looks like. And we cannot understand exactly how it works and what dynamics it drives it. But here, if we get rid of the noise, it's much cleaner. We can see coherent structures, which are large patterns that repeat themselves, and consistent dynamics of the flow. There are two ways to extract this coherent structure. One way is data-driven methods, which are time-stepping methods deriving the full nonlinear equation, which is really accurate but data-heavy. Another way is to use low-order models, and this is the route that FELiCS uses, where we just linearize our equation, we drop the higher fluctuations, and we do all this instead of the time domain in the frequency domain. So what we lose is some accuracy, but what we gain is results that can show us the dynamics of the flow. And in the next slide, I'm going to present you a little bit what these linearized methods are. So in the first step, you have your system, which could be chaotic, multi-scale flows with complex geometries. Of course, here I chose a 2D laminar flow, just to show that to you, but later on I have more applications. And on the second step, what you do is we derive the mean flow, which is the time average flow, and the fluctuations. And we assume that the fluctuations, so the perturbations, are really small. So from the mean flow, then, we try to find the dynamics. And we ask ourselves, what happens to our system if we put an external force to it? How does it respond? Or what are the largest energy locations in our system? And as you can see here, we can also extract the coherent structures, so these patterns. On the first image, we have the CFD simulation. And on the second image, we have the linearized model. And as we can see, we can capture the coherent structures really good only with the mean flow. And the last step is then to control our turbulence. And we can do that by shape optimization, or finding where the instability is. And all these are what FELiCS has in its structure. And FELiCS is for every user. As I said before, we were a really different expertise level team, so we just tried to capture this. So if you know your engineering stuff, but you don't want to use Python, you can use it as a monolithic user. Just run JSON files, and that's it. Or you can build around it. You can import it as a Python package. And finally, if you see that things are missing in FELiCS, you can just add the new geometries or the new solutions without changing anything from the framework. And let's make a deep dive into each user. So for the monolithic user, you need just a grid, which can be 2D, 3D, structured, unstructured, whatever you want, a temporal mean field or a fixed point solution, and the configuration files, where you set your boundary conditions and your finite elements. And this, you throw everything to FELiCS, and what you get is either a coherent structure or the collection of all solutions of your space, how unstable or stable your system is. Now, taking a step further, you can import FELiCS as a Python package. And here you can see also how FEniCS is used, because you can set up and import your mesh, use the equations. Right now we have mass, momentum, energy, and species equations. And finally, you can import the linear solver, which is due with Slepsy and Petsy. And from the results, you can build around it either through doing data simulation, optimization loops, or even your own post-processing. And if you think that, there are things mixing, but if you find something that isn't included in FELiCS for your setup, what you can do is add new geometries, new spaces, new physics, without rewriting all the equation. Because we did it modular, so you just need to add the spaces that you want or the physics that you want, and without changing the framework at all. And now some more complicated applications that we did through the years with FELiCS, from trying to predict what happens when methane comes in oxygen, how unstable our engine is, from finding the instabilities in Francis turbine, predicting thermoacoustic noise at the end of the airfoil. And finally, our last publication is a 3D setup. And what we try to do here is finding the breathing motion, where the flow and the geometry just is not one another. And I'm going to go a little bit further to this publication. So this is our setup. And what we want to predict is exactly this area here. And we want to identify this breathing motion because this is where many fatigue or noise problems exist in engines, and this happens in really low frequencies. And as you can see, we predicted that pretty well. And low frequencies is really important in that case because in order to do this in time-stepping method, it needs a lot of time. And here we did it just in seconds using the mean flow. So all in all, what FELiCS tries to do is to bridge the academic linear analysis with engineering applications and real-world multiphysics. And we have different applications to do that, from combustion instabilities, airfoil, aeroacoustics, water turbines instabilities. We have an embedded post-processing inside the FM framework. And we have also documentation, multiple test cases that you can use. And if you want to take a look at our documentation and our project, you can scan our QR code or see it at FELiCS.eu. And yes, thank you so much for your attention. Are there any questions?
Thank you very much. Great presentation. While we're taking questions, maybe the next speaker can prepare so we get a kind of a pipeline. And are there any questions from the audience? Yes, please.
Yes.
You didn't show how you linearize the Navier-Stokes equation.
We do that. That's true. I have it.
I mean, the turbulent flow is nonlinear by nature. How do you do that?
Here, you say everything second order goes away because these non-linear terms are not the ones that drive the system. So you just linearize it and drop them. And you take only the mean flow.
Okay, but the source is nonlinear by nature?
Yes.
And where it goes?
But we don't study this in our group. And we don't want to substitute the methods that are nonlinear. What we do is we try to use less data to find the instabilities, not simulate the flow.
Because the instability is more acoustic than the dynamics, maybe?
It's acoustic. It can be also a pressure instability.
Yes.
Yeah.
Great. More questions? Yes, please.
Is this Reynolds Navier-Stokes or
Sorry, no.
is this Reynolds Navier-Stokes?
Yes.
Okay,
Yeah.
More questions? So maybe I can take the opportunity. So I will speak later today on also on aerodynamics and turbulence. And so you say it's heavy to sort of directly solve the equations, but I will show that. So we don't think it's heavy, but so maybe there can be a sort of interest. But I think of course it's always interesting to make it cheaper. You can always make it cheaper like this. And so we're working with the aerospace industry, with Saab in Sweden, for example. And one application is aeroelasticity, and they are super fond of linearized models. So have you studied, have you looked into those applications, like fluid structure interaction and airfoil bending, for example?
Yes, and we are preparing also a publication next month for this.
Great, so maybe we can speak in the break or something.
Yeah, sure.
Yeah, perfect. Any more questions? Otherwise, I think we thank the speaker again. Thank you very much.
Thank you.